So for kinetic energy, okay, for kinetic energy, it's not that we're lifting something up, right? When we gave something potential energy, we took it and just changed its elevation, yes? Okay. For kinetic energy, if I give something kinetic energy, the simplest case is that I just speed it up horizontally somehow, right? I don't lift it up. I just take it from rest to some speed. Yeah? Okay. And so the force is a force that speeds the thing up. And so I'm going to do the same thing. I'm going to say that the energy is the work I do on the ball. So work is force times distance, right? Now, I'm going to substitute ma in for force. Is everybody okay with that? Yes. Are you okay? No. Are you okay? I want to make sure everybody's okay with that. Because I don't want anybody to be mad. Thank you. There we go. And then the problem is that A and D are history-dependent things. And I think I tried to demonstrate that potential energy was not history-dependent. In other words, it didn't matter how the mass got to the table. It just was the height of the table and the mass of the mass. Yes? Okay, that matters. The same thing is true for a baseball. If it comes flying back in, if some kid out there gets mad and throws that Nerf ball back in here, how much it hurts me depends on the mass of the ball and the velocity and nothing else. It doesn't matter whether they sped it up in a quick snap, right? They could have had something that sped it up over this much distance with an incredible acceleration or this much distance with their arm. It doesn't matter, does it? It's the mass and the velocity, right? And this is the acceleration, there's the distance. There's got to be a way to get rid of it. Well, here's the way. Because what Vf squared is Vi squared plus 2a times x. Well, this x is really d, yes? X is distance. The initial velocity was 0, wasn't it? I start the ball at 0 velocity so that all the work I do on it is its kinetic energy, right? And then I'm going to take off the f because it's the final velocity and it'll look nicer. And then let's see, what do we do? I think what I want to do is go v squared over 2. Isn't that just a times d? Yeah, that's beautiful, right? So now let's keep going. MAD becomes mv squared over 2. That was beautiful. Isn't that beautiful? Is everybody okay with that substitution? Because I don't want you getting moved 2. That one's not as funny. Or maybe it's funnier, right? Move. I can't even say it. Right. So this is how people write it. They write Ke equals 1/2 mv squared. You might have seen this in driver's ed. They have this whole thing about how if you double the mass or the velocity of the car, you quadruple the destructive ability of the car. I think you saw you saw a graph. I'm getting all emotional. Right, and this is why it is if you make a graph of kinetic energy versus velocity, it's a parabola, and going from 30 to 60, right, is you're actually quadrupling the amount of destructive power. If you double the mass of the car, you only double the energy, right? So this is the rationale. The U.S. military adopted high velocity rounds. The M16 is a really small caliber rifle, but they shoot really fast. And the notion was you don't want to carry around a lot of extra weight in ammunition because the velocity is more important, right? Does this kind of make sense? Whereas the AK-47 is a bigger shell, but it goes slower, right, to accomplish the same thing. And this is all well and fine unless you are trying to shoot through like debris, like in a jungle. If a high velocity round hits a twig on its way to the target, well, gee, it's going really fast, right? So air friction is a very significant factor in it, especially since it doesn't have much mass, right? And so if it just hits the smallest thing, it's going to go way off target, right? And that was one of the problems they had in the Vietnam War with the M16, was it didn't do so well there. But anyway, there we have it, right? We've got a formula. And this is in joules as well, right? V is velocity, m is mass. This is kinetic energy in joules. And so if I double the kinetic energy of this hammerhead, do I double its velocity? It's going faster if I double it, but did I double the velocity if I double the energy? Well, no, because if I double the velocity, what happens if you square something that's doubled, you get 4 times the energy, yeah? So it's actually what? If I double the energy, it's actually what? Square root of 2, which is a number bigger than 1, right? Increase, whatever that is, right? What's up, you guys? There are 2 ways to speed up the math, right? The first way is, and then I don't know, was it your class, Jen, where I went to speed it up, and I tried to do like and then throw it, yeah? And I hit this trophy above the door, and it jammed in the trophy. I'm not going to try to do this again because I think I would break something. But there it was. It's like, no, I think I need some applause for that shot, right? And it took a little bit of the fluff of the severed timber wolf and jammed it in there too. Jeez. Let's try these. What is the kinetic energy of this is, by the way, a bullet that would hunt a tank, I think, or an airplane. 230 grams. A bullet might be 2 grams, 3 grams, 4 grams for a big one.